Are you ready for definite integrals? Definitely. This is out of 18H, and it's not too bad considering you were just doing U substitution. So here we go. We've been taking indefinite integrals, which is the same sort of thing as this, but not from one spot to another. We've just been taking the integral of f of x dx, and it gives us an equation to describe the area at any x value, from any x value down to 0, right? So far this gives you an equation to talk about area. And sometimes you just need to actually find the area, and we do that with the definite integral. We talk about the area from one spot to another. Yeah, so this reads f of x dx, we integrate from a, the lower limit, to b, the upper limit, with respect to x. And so that sounds a little daunting, but it's not. You know that from 0 to 3, if you integrated this, right, you could find the area under here, right, from 3 down, down to 0. And if we wanted something like this, from 1 to 3, you could just find the limit from 0 to 3, it's all of this stuff, and 0 to 1, it's all of this stuff, and you would just cut out this piece from here, right? You just omit this, and what you'd be left over with is this section, and this piece is the integral from 1 to 3 of root x. Right? So here, this piece that we have, this whole chunk, is the integral from 0 to 3 because it's telling us the area from 3 down. This chunk is the smaller portion from 0 to 1, and if you subtract them, you get just the area from 1 to 3. It's called a definite integral. It doesn't have to go, it can sometimes go from 0 up, right, and that's fine, but it's from one specific x value to another specific x value. Also, integrals can be positive and negative. The integral is the area between the curve and the x-axis. So if you're adding up all the areas, if you're talking about the integral of this, I don't know, sine curve, some of it is positive because it's above the x-axis, and some of it's below the x-axis. You're adding all of them up. You're adding all the pieces up. You're summing, right? The s, the stretched out s that is the integral sign, just means the sum of this rectangle, trapezoid, that trapezoid, and all of these, right? So if you have more positive than negative, you're going to have a positive net area. There's more here than there is there. And if you have more negative net than there is positive, you have a negative net area. There's some fun pieces on Desmos if you want to play with this. But there's 4 fancy rules about definite integrals. They're here if you want to write them down. Ping, 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 ping. They make sense if you look at them right, so I just wanted to show you each one. This is sort of a visual that helps, that I hold in my brain when I'm working with integrals. So here's the first rule, is if you're going from A to B, you get the opposite if you go from B to A, if you switch those. So think about this. This is the integral of root x dx going from 1 to 3. If you're going from 1 to 3, you'd take 3, the area from 0 to 3, and you'd subtract the area from 0 to 1. You'd subtract this piece just like we did in that first part, and you'd be left with 1 to 3. I took the liberty of calculating those values, and from 0 to 3, the area under the curve was this, 3.5, and in the 0 to 1, the area under the curve was this, 0.66, so this and this. And so if you were trying to find just this piece from 1 to 3, this definite integral, you'd subtract them. Yeah, you'd say the 0 to 3 minus the 0 to 1. and so it gave us this. If you flip these around, notice we're going from 1 to 3, and here, if we wanted to find from 3 to 1, you do the same thing, but your subtraction is backwards. So instead of big number minus small number, you're going small number minus big number, and you get the exact same value, it just has the opposite sign on it. Right? So I just think about small number minus big number should give me the opposite, and that's kind of what I keep in my head. If not, that's hopefully in your notes and you can reference it. This is the second piece. If you have a constant inside the integral being multiplied by a function, you can just peel the constant outside and integrate the function and then multiply. And that works because of this. Here's f of x, and we're using the root function, just root x. If you took the integral of this, if we integrated this, and I'm not necessarily going to do it from definite integrals, but I guess this would be from 0 to 4 and 0 to 4. You can see that this is the area underneath this curve. So it's like these blocks and these blocks. I'm going to actually make them rectangular, right? Those, right? And you'd just be adding up the blocks, essentially. If you instead had f of 2x, right, and you were integrating that between 0 and 4, you're finding the area again, and really the area is here. Look, we have double the height as this piece, and double the height as this previous blue piece, and double the height, and double the height, and double the height. So we have double the area, right? So instead of integrating this inside, you take the 2 and you pull it outside, right? And it makes a nicer integration for us. So this is really 2 times the integral of the root x. It's 2 times this one, right? We get the area by multiplying the height of the boxes, right, by the base, and our height has doubled. So all you need to do is double your original area here, and you get the area of, running out of colors, you get the area of the whole thing. You get the area of all this. But short version is, if it's inside, you can pull it outside if it's a constant. This piece, pretty straightforward also. If you're going from A to C, if you're integrating from A all the way to C, it's the same as integrating from A to somewhere in the middle and adding that to that somewhere in the middle to the endpoint C, right? So from going A to B plus B to C, those areas will add up to the area from A to C, right? So this looks like a lot of mumbo jumbo jargon, but it's just like you're adding areas up. It's geometry. Neat. All right, and for the last piece of this, you'll often see an addition of functions inside. You can kind of piece them apart in your head and think about them as 2 different functions. If you're integrating, you can integrate the first component and add it to the integration of the second component, the function. And this is kind of how I think about that. You got 2 functions, and this function is n. It's this blue line. So this is n of x, and this is m of x. This guy, m of x. If you're integrating, it really means you're adding the areas underneath like this. You could think of this, okay, and this purple, sorry, this purple is the sum of the 2. This is f of x, which is n of x and plus m of x. If you're integrating this, right, if you're integrating this addition, you're really just, these are y values, and you're adding up, you're asking how tall is this rectangle, right? Well, that rectangle height is the sum of this line, the m of x, and adding to that the sum of, or adding to that the height from here, right? So you're adding the red to the blue. Let's do it this way. Let's move the red up. And that's where you get that height from the of the purple. I'm not good with colors. Same thing here. If you're adding up this, right? I want to know how tall that rectangle is. You take the height of the first line. The height is the y value. It's m of x, right? And add it to the height of this blue line, which is n of x. And if you add those up, you get the purple, the height of the purple line, right? And so you're just adding up the area underneath each of the curves independently and putting them together. And I sort of view that as the y values. You could also think about it as just you're adding this. Let's see, it would be that. This is why I don't visualize it like this. That plus this piece. And if you added up all those boxes and put them in a certain way, I wonder if I can grab the this piece. That you'd have to kind of weasel that in there, but that should fit somehow like that. It's another way to maybe look at it. So those are the 4 pieces, and here they are sort of in snapshot format. So enough talk, let's use them. So if you're finding the definite integral of this, first you integrate, right? So when you integrate the inside, don't worry about the outside brackets, just look at the inside for now. This we integrated, I know the exponent kicked up by 1, and we multiplied 1/3 out there, and then same thing. And so now we've got our integral inside. Just as an aside, what happened to the plus c? Where's the plus c? You don't see it. It's not there. Go ahead and put it in if you want, and it'll look like this. Here's just an example. If you were integrating this, I don't know, 1 to 3, 2x dx, and you felt compelled, this should be x squared, and you're like, where's my c? Gotta put the c in. There's the c, 1 to 3. If you were, I know we subtract these, we evaluate at 3, so this would be 3 squared, 9, plus c. I don't know what c is. Who cares what it is? Right? I don't know what it is. And we subtract, put the 1 in there, right? And you get 1 squared, 1, plus c. It's the same c, right? Well, we're distributing this. So this ends up being 9 plus c minus 1 minus c. And the c's go away regardless of what they are, regardless of what you've integrated. When you put plus c in an indefinite integral, you're subtracting, and by definition you're going to subtract the c's and gone, right? So go ahead, put the c in, but it's just a waste of time. Cool? Ching. Now let's get back to it. I know we're going from 1 to 3, and so I'm going to first find the integral from 0 to 3, and then from 0 to 1, and subtract them. So this piece is the integral from 0 to 3, right? And all you do is plug a 3 into there and there. So we got 3 cubed over 3 and 2 plus 3. And then we're going to do the same for this piece. This piece is just that integral from 0 to 1. And you just plug 1's in for the x's into there and there. And you crunch the numbers together and solve, right? This becomes 9 plus 6, this becomes a third plus 2, and you subtract them. And you get 12 and 2/3. Cool. The mechanics are pretty straightforward. The integration can get tricky, but you can always check it because on your fancy calculator, there's a function for doing this, finding definite integrals. So let me pull up my fancy calculator. Clear it out. Clear, clear, clear. All right, and it should look like this. If you were trying to find the integral from 2 to 5 of x e to the x dx, you can ask your calculator to calculate the specific value for that. It won't necessarily give you the equation, but it'll just spit out the value, and you run it like this. Here's if you want to shorthand it there, but everything good in life is in the math button, and then you have to go down, 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 down to number 9, function integration, int, enter, and it gives you this beautiful setup. Man, so we're going to plug in 2. You have to go up. It's a little bit obnoxious. Hit 5, right? 2 and 5 over, and then x. I often will just put the multiply by, and then you could go second e to the x, or however you like to put that in. You also need to put the x here, dx. We're differentiating with respect to x, and the calculator needs to know that. And then you just say go, baby, go, and it pops out that for you. Amazing. Kiss that beauty. Thank you. Neat. This is with my fancy TI 84 Plus Silver Edition. My TI 83 does it a little bit differently, and so if you have other models, this is how to run them. Oh, not those kind of other models. Other models with calculators. There you go. So here's with Casio. Here's with a older TI 84 or TI 83. It doesn't give you this beautiful setup. Sometimes you have to plug it in a little bit of a different way, and an Inspire. There you go. So let's do one more set of problems, and then we'll call it a day. Let's do the math. Get out of here, kitty. So for integrating this, we're going to do the same sort of thing. I know that the integral of sine of x is opposite of cosine x, negative cosine x, integrating from 0 to pi thirds. And so we're going to evaluate at pi thirds the integral, and then we're going to evaluate the integral at 0 and subtract them. So we plug this in for pi thirds, we plug it in for 0. We say, all right, well, this is a half. This is from our trig extensive trig knowledge, and this is 1, and then you add them up. And you could ask your calculator the same thing, and it should give you 0.5. Let's do one more. We want to integrate this mess, which means we'll integrate the pieces separately. When you integrate the 2x, the exponent should be a 2. The exponent should be a 2. That's where this comes from. There should be a 1/2 in front, because you put the reciprocal of the new exponent, and the half and the 2 multiply, and that's why you don't see anything there. Likewise, this is 3 times 1 over x. Leave the constant, integrate this piece, and that's natural log of x. We're going to evaluate all of those. This completely at x is 4, and then again at x is 1, and then subtract them. And that's what this mess is. All right, here we put 4 in here and here, voila. And then we put, here we put 1 in here, and voila. And then clean it up. Clean it up. So the negative distributes in there and there. So this is going to be 15. And then, oh, I bet they do. I bet they do this. So my guess is this is 15. And then this part, this natural log, is going to be, I bet, like this. 3 natural log of 4 minus 3 natural log of 1. Natural log of 1 is log base e of 1, which really means e to what power gives you 1? 0. So this is 0, so this is 0. So this is 0 times 3, so this whole part goes away. Sorry, Charlie. So this doesn't matter anymore. And then natural log of 4, you could probably clean that up. I bet they clean that up. I'd clean that up. So then this is 3. Natural log of 4 you can call natural log of 2 squared. And then the 2 can come outside. Yeah, and you get 2 times, you get 3 times 2 natural log of 2. Remember, that's that exponent trick. And so then this should be 6. That's my guess. That's my guess. Gorkevich out.